And then we have come to the final talk of this workshop. So, and the final speaker, we are lucky to have Hongyang or Ryan Zhang, who just joined Northeastern University as an assistant professor of computer science. So he obtained his PhD from Stanford last year, and he was a postdoctoral fellow at Penn for 1 year. And so he's done a number of very interesting and deep works on theoretical machine learning, including one paper on matrix sensing that got the Best Paper Award at COLT in 2018. So if you are here and you can try to share your screen, Ryan. Is Ryan here? Oh, he is here, but he is here as an attendee. Let me promote him to a panelist. Okay, so he is now a panelist. And let's see if he can. All right. Yeah. So let's see if you can share your screen.
Yeah. Can you see the screen?
Yes, and if you can magnify it so that it's full screen, that would be great. And so today he's going to talk about generalization effects of linear transformations in data augmentation.
Great. Okay, yeah. Thanks to Edgar for the kind introduction, and I enjoyed the workshop so far. So hi everyone. So my work focuses on algorithms and theoretical aspects of neural network learning, with supervision such as data augmentation and so on. And today I'm going to talk about our recent attempt to develop some theory for data augmentation, and hopefully some of the theory provides new insight to practice. The talk is based on joint work with Seng Wu, Greg Valiant, and Chris Ray that appeared in ICML this year. So if you have any questions or if anything is not clear, please feel free to ask at any time during the talk. Okay, so as you have seen repeatedly earlier today, data augmentation is a technique that generates new labeled data easily. So many recent works in the deep learning community have found data augmentation very useful. So I guess part of the reason is probably that data augmentation is one of the techniques that can produce large amounts of labeled data automatically. And as you probably know, getting labeled data is typically a bottleneck of neural network training. So for example, so just to give some a bit more specific, on the right-hand side here is a original quokka image. Using data augmentation, we can generate new images that change the color, position, or contrast of the image. So in image classification, data augmentation has become a standard practice. So I just want to take a minute to reflect here. Why is data augmentation useful? Well, so there's this very nice survey from last year in particular. So one of the folklore beliefs seems to be that just by adding more labeled data, the model somehow generalizes better to unseen data. In other words, maybe the augmentation function created a new sample that somehow matches the test data set more accurately. So on the other hand, data augmentation does not really fall into any classical statistical learning framework because the added data distribution might be very different from the training data distribution. For example, the added data distribution might depend on the transformations we use to generate the data. So this is so just to set up the context for my talk. Our work's goal is to seek a theoretical framework to understand data augmentation better within this context. As part of our effort, we also propose a new algorithm that selects useful transformations more efficiently via a biased sampling procedure. So in the next couple of slides, I will give you an overview of our work before diving into the specifics. So let me begin by describing a typical data augmentation pipeline. For example, suppose our goal is to build a classifier that predicts whether, so let's say there's a quokka in the image or not. Using data augmentation, we can create many images, many similar images, just by transforming the original image. And then we perform a backpropagation over the changed images throughout the network to update the parameters. So as you can see here in the middle, there are many ways to change the image. It seems that we have solved the problem of getting labeled data. However, the problem is that some transformations may not be very useful. And this also depends on the dataset and the prediction task. So there was a very nice example from one of the speakers earlier today. So let's say you want to build a model to detect cars, then it might be a bad idea to flip the car upside down. So maybe one naive way is to try a brute force search over all the possible transformations, but this is going to be pretty expensive because the search space is quite large. And furthermore, with composition or combining multiple transformations together, such as change the color and the contrast simultaneously, the search space grows quadratically, and so which become pretty large very quickly. So this is the problem of augmentation search, and there have been a number of prior approaches that address this problem. One of the earliest approaches uses a generator discriminator framework similar to Gang's. The idea here is that the discriminator is trying to classify the image accurately, whereas the generator is trying to create images that the model does not recognize. The parameters of this framework are optimized through an RO-based search process. These approaches have produced superior empirical results with a caveat that the computational cost can be relatively high. So to reduce computation, a team from Google Brain proposed a very beautiful idea last year. So just to randomly sample transformations. In other words, so let's say you have a million parameter options for the transformation. So their idea is just to randomly sample one of the million transformations uniformly. And it turned out that this actually gives you very competitive results. So we will get back to this idea a bit later in the talk as well. So also from last year, a third approach uses Bayesian optimization. Roughly, so these works borrow ideas from the area of hyperparameter optimization to search for transformations. And finally, a paper that appeared in iClear this year introduced a pretty sophisticated adversarial training approach that actually achieves the state-of-the-art results on multiple image benchmark datasets. So you can see that there have been lots of efforts in designing ingenious space in this ingenious methods in this space. And the question that motivated our work is that it seems to us that a principled understanding of these transformations and when these techniques work well seems mostly unexplored. And our work will talk about this question. So in particular, so we will consider a theoretical framework that focuses on linear transformations. So we study three categories of linear transformations. First, so we have what we call label invariant transformations, such as rotation and horizontal flip. And so it's not hard to see that these transformations, so you can write it as a linear matrix product over the input given these for both operations. And note that these transformations change the input features, but keep the labels the same. And second, we consider a mix-up, which so Greg talked about earlier during the panel discussion. So this is a very exciting technique proposed by Zhang et al. In 2017. So what this mix-up transformation does is given a polka image and a dog, mix-up produces a new sample that randomly mixes the two animals. And the label also becomes a mixture of polka and dog. And third, we have compositions of transformations, such as applying rotation and mix-up together. So in our theoretical framework, we consider an over-parameterized linear regression setting that I will talk about in the next slide, and study how adding new samples impacts generalization. So, and also we like to validate our theoretical framework. Therefore, so we consider two metrics that measure the effects of applying a transformation. And I will talk about it later in more detail as well. So here's the formulation for our setup. So we consider an over-parameterized linear regression setting where the number of parameters in the model is greater than the number of samples. So in other words, so this is an underdetermined linear system. So this the reason why we consider this setting is because this captures the need for adding more data in these data augmentation scenarios. So we have a training data set. The feature vectors are given by p-dimensional vectors x1 up to xn, and we assume a linear model where the labels are equal to the features times a linear model plus noise. Recall from the last slide that we want to model linear transformations. So then, we go over them one by one. For a label invariant transformation, denoted by a matrix F, the transformed sample feature is simply F times X, and the label is still the same. For mix-up, recall that it acts over two samples, X1, Y1, and X2, Y2. And the mix-up sample is basically a linear mixture of the two samples. So it has this linear combination form with a mixing parameter or mixing fraction parameter alpha. And finally, for the composition of two label invariant transformations, F1 and F2, the transformed sample has feature vector F1 times X, F2 times X, and the label is still the same Y here. So we're going to study the ridge estimator in this setting with the regularization parameter lambda, and we ask the following question. How does adding transformed samples using the above transformations impact the ridge estimator's generalization error? In other words, so the spirit that we're really trying to capture here is, so as you have seen that, so data augmentation seems to be really useful in practice. So we really like to capture whether we can show that for certain types of transformations, adding these transformed samples gives a provable benefit over the baseline. And we like to get some intuition about so when can we get these provable improvement and how it might depend on the transformation function. So instead, so I guess here we're not going to provide an end-to-end theory of using augmentation on neural networks, and that is certainly an interesting direction for future work. So okay, so now we're ready to describe our results. So our first result is that so let's consider a label invariant transformation F, and let's say that we add a transformed sample of Fx with label Y into the ridge estimator. Then we can show that actually this does provably reduce the estimation error of the ridge estimator by a rate proportional to the following. So roughly what this quantity highlighted in the red color here is, so you can think of it as the amount of a direction or the amount of a new signal that is added to the span of the training data points. So yeah, and the reason why so we get this kind of result is that because we assume that the number of samples is less than the dimension. So therefore, so when you add a direction that's not in the span, this covers some new direction in the space. So our next result is for the mix-up transformation. We show that mix-up plays a regularization effect that shrinks the weight of the training data relative to the regularization parameter. And so, so I want to give you some intuition about what's going on here. So if you just take my my word for it, and it's not hard to verify later, so we can write the covariance of the augmented mix-up sample as the following equation. So in expectation, recall that the mix-up sample picks two samples x1 and x2 uniformly at random from the training data set. So you can show that the expectation of the covariance is equal to this scalar, which is 1 minus 2 alpha square, where alpha is the mixing fraction of the mix-up sample, times the sample covariance of the original training data. And just by combining this equation, we then get that the expected covariance of the augmented sample set is the following. So it turned out that the sample covariance of the augmented set is now has a weight that is smaller than the original sample covariance. In other words, so just by adding this mix-up sample, we have automatically shrunk the weight of the sample covariance of the training data. So, so finally, so we can also show that for the composition of two label invariant transformations, they give you a provable benefit that's roughly similar to the base case of just having one invariant transformation. And the intuition here is that by combining multiple transformations, this further expands the space space of search. So okay, so yeah, so in the next slide, so so just to recap here, so what we have here so far. So we have shown a couple intuition about so why adding transformed samples can reduce the estimation error of the risk estimator. And the next question that we'd like to ask is how do you actually measure these intuition in a more practical scenario? And our idea here is that so we like to separate the predicted labels randomness from the deterministic part. In other words, so I mean, we have these intuition about some transformations adding new information and some has a regularization effect. So here what we like to do is we want to separate the randomness of the predicted label from the deterministic part, which we sort of think of it as the amount of information in the data set. So in order to do this, we train an ensemble of neural network models. Using the ensemble, we take the majority label as our prediction. So here, so I just have a toy example. So let's say we have an ensemble of 5 predicted labels, then the majority label is plus. So based on this ensemble, we consider or we measure 2 scores. So one we call the error score, which measures the accuracy of the majority label compared to the true label. So in the example here, so the majority label turned out to be correct. And a second score that we measure is the instability, which measures the fraction of mislabels of the majority label compared to the ensemble. So here we have the instability score of 40% because there are two incorrect labels within the ensemble. So so our first observation, so we did this experiment on MNIST. you can see that for several label invariant transformations such as cutout, which basically cuts a small piece of the image, or random cropping, or rotation. So these transformations all reduce the error score of compared to the baseline. So you can see that there's some amount of drop in the error score here. So we take this as a validation that these invariant transformations indeed add some new information which is not accounted for by the randomness in the training process. And so our next observation is that so we measure the so recall that we have this intuition that mix-up has a regularization effect. So we measure the instability score of using mix-up compared to the baseline. And we observed that as we increase the mixing fraction of same class digits, so there's some details going on here. So in other words, what we're saying here is that if we mix more ones with ones and twos with twos, then this can improve the stability of the prediction. And finally, so we also investigated the role of composition on MNIST, and here is some observation we have. So we found that actually on MNIST, adding translations on top of let's say rotate, cutout, and random cropping does not improve the performance of the model anymore. Or in other words, so translations do not seem to add new information. And this makes intuitive sense because if you rotate the digits by a small degree, just using rotation, it sort of covers various position that you would expect to get from translations. So next, inspired by our intuition that you know, like the amount of gain you get from an augmented sample depends on like how much information it provides, we propose an uncertainty-based augmentation sampling algorithm. So this is roughly how our algorithm works. In the first step, the users provide a list of transformation functions, such as rotate or invert, and so on. Then in the next step, based on these transformation functions, we're going to generate k different transform samples. In other words, so we randomly sample these transformations to apply on the original image and create multiple transform samples. And the next step is that the model will inspect the loss of the transformed samples using the current parameters of the model. So after inspecting the losses, we're going to keep the ones that have the highest losses, let's say the top two or top one, and so on. And we're going to discard the ones with the smallest losses. So once we keep the ones with the largest losses, we perform a back propagation to update the parameters of the network using these transformed samples. So in other words, so what we're doing here is we're trying to pick samples that the model has not learned yet because they have large losses, and we're not going to keep learning from the sample that already have small losses. So as a remark here, the idea we have here is sort of conceptually similar to the work of adversarial auto-augment, whereas we have this simpler pipeline of just having to do random sampling and the inference without having to train an adversarial network entirely from scratch. So we evaluate our method for multiple image classification benchmarks and architectures. So here are some highlights of our results. For example, so we ran our algorithm on EPNet, and we get similar or comparable results to the state of the art but we use less computation. And another highlight is that if we increase the number of augmented samples, if you recall here, here we have the option of choosing of having more samples, keeping more samples, or keeping less samples. So we found that if we increase the number of augmented samples, this further improves the accuracy of the trained model. So why does this method work? So here are some ablation studies we have. Well, the critical insight that enables these results are as follows. So here's what we observe. So first, for some kinds of transformations, such as here as the blue line here shows, first do a translation over the y-axis and then do a cutout. So our method gradually reduces the frequency of these kind of transformations, just because the loss of these transformed samples has reduced, and therefore the model is no longer going to do the update over these samples. On the other hand, there are other kinds of transformations, such as mix-up, because it just produces samples with large losses that the model cannot learn. And for these samples, the frequency increase because just because of the way the method works. So this roughly concludes our work. And so here's a quick takeaway. In our work, we provide a theoretical framework to understand data augmentation better, and we propose a new augmentation sampling algorithm. Some of the key intuition that we learned from our theory is that label invariant transformations add new information to the model, whereas label mixing transformation, such as mix-up, has a regularization effect. So here are some more links if you want to learn more about our work. So we have a blog post online that describes this work a bit more informally, and also we released the code if you would like to try it. So finally, I just want to have a discussion about some ongoing and future work. So first, so as you can see here, our results here are heavily anchored on image classification, but we are very excited about using it for natural language processing as well. So for example, so a subset of authors and collaborators of this work recently applied ingenious augmentation methods to the task of named entity recognition. And finally, another direction that we're very excited about is how do you think about the model robustness in this context of data augmentation? So as you can see here, so there are many things going on just by adding transformed samples and all sorts of hyperparameter search. So it's not clear, if you're going to let's say deploy these kind of methods in a practical context, how robust would it be to outliers? And in particular, so there's this other work from our group that studies the so-called subgroup performance gap, which is so in other words, let's say there are different kinds of age distributions, and we want to make sure that our model is providing a fair comparison over all the age groups. So yeah, so that concludes my talk, and that's all I have. Yeah, thanks for your attention.
Thank you very much for the great talk. So now's the time to ask questions. There's a few already right here. So anonymous type question: if you keep retaining transformations with high losses, do you end up with counterproductive transformations, like rotating white 180 degrees, which turns 9 to 6 and leads to high loss, but not to a better data set?
Yeah, so I mean, so we certainly observed that, and so I think our So our answer to that is, so in some sense, so you do want to keep some of the samples with large losses because maybe there's some information there. This kind of like the exploration versus exploitation trade-off. So maybe you do want to explore those samples with large losses a bit. But yeah, so eventually at some point, so these samples are going to occupy most of the augmented samples just because the model does not really know how to learn from these samples. Yeah, I don't know if that answers the question.
Yeah, I think it's helpful, and if there's if the speaker, if the person who has the question has more questions, then they can contact you. Another quick question from David: is there a connection to multi-arm bandits? Some clean connection?
So yeah, I think that's a great question. So I think some of the approaches used in Bayesian optimization indeed is heavily inspired by this line of work from multi-arm bandit. Our method is sort of simpler than that. You can imagine is some kind of uncertainty sampling, which is I guess very popular in active learning. So in some sense, I would say that it has this spirit of trying to do the greedy selection, but a bit simpler. But yeah, I would imagine it might be interesting to explore this kind of idea more, a bit more in this context in future work. Yeah.
Great, thank you. And actually, I also have a question, and just very quickly, and maybe some other people posted, but just in the slide where you had all the theoretical results. So did you keep the same lambda after you added new data points? Because we know in general for ridge regression, the choice of lambda is crucial. And if you have different data, a different lambda may be optimal. So what I would be very interested to see is like the optimal lambda for n, how does that perform with respect to the optimal lambda with respect to n+1? That I think would be a strong result. I don't know if you consider that.
Yeah, so that's certainly a great question. So I think, yeah, so actually going back to your question, so I'm not sure if we are able to show that. So I think, so what we're saying here is roughly like, so this adding this mix-up sample is sort of equivalent to reweighting the training data and the ridge regression parameter. In other words, if you're going to optimally tune them, so you can probably get the same performance here. So, but yeah, but here we're keeping the lambda parameter the same. Yeah, it's a great question, and yeah, I think it'll be interesting to see if there's a context where like you're saying, if you can optimally tune the ridge regression parameter to maybe is there still approval benefit there? And I don't quite know the answer. Yeah.
So the person who posted, thank you, the person who posted the previous question asked, so do you keep a priority in the transformations?
So yeah, so initially we just have a uniform prior. So in other words, we don't have priorities. But as the network gradually progresses, then as you can see here, for some transformations, their losses are going to decrease. So therefore, those transformations will have lower priority. But we do keep a uniform prior throughout the algorithm. Yeah.
Okay, great. So I think that there are no more questions posted. So with that, we conclude our workshop. I'd like to thank all the speakers for presenting their work and all the attendees for attending and engaging with the workshop. So, and I really hope that we can, like Costa said, we can build some sort of community around this set of exciting topics, which are registering a lot of progress. And I think there's a consensus emerging here that they're important. So thank you very much, everybody. Costas, if you have a few words.
Yes, this was really a set of amazing talks. I mean, also because I attended the whole day, but I learned more than in the whole ICML and ICLR and CBPR in the previous months. Thank you very much, guys. This was really very, very informative and very stimulating.
Great. Thank you very much, everybody. Have a nice rest of the day, and hope to interact with you soon. Bye-bye.
Bye-bye.
Thank you.